All right, so in this problem, we want to write an equation for slope and displacement in this beam. And I like these just because I don't have to worry about numbers. So I'll just saying that the intensity of this loading is W, and that'll just be in force per unit length. And the beam is a simple span of L. And you can see here at A, we have a pin connection. So do we know anything about slope and displacement at a pin? What's the displacement there?
It will rotate.
It will rotate, but it will not displace. So we know the displacement is 0. We don't know what the slope is. Now over here at B, what do we know?
It will rotate.
It still will rotate, but it will not displace. We're talking about displacement in the vertical direction. We're not looking at horizontal displacement.
Oh.
This thing will displace horizontally. So we're not concerned about that right now. So we're looking at just just the displacement generated by bending moment. As we get more sophisticated, we'll come back and add displacements based on axial force and shear force. But right now, we're just going to start with the one that dominates. Usually in a beam, bending is the one that dominates and generates the most displacement. So our technique that we have right now is direct integration, so we have to be able to write a expression for moment in this beam. So let's do that. I guess the first question to ask you, or to ask yourself, is can you write one equation for moment in the beam?
Yes.
The answer is yes. You can see the load is continuous, so we should be able to find the moment. So let's do that. So I'm going to cheat a little bit here and write that I've got a reaction here at Y and a reaction here at B. And then to be able to find these reactions, I'm going to come up with a concentrated equivalent force for the whole distributed loading. And that would be what? Well, it would be the area under the curve describing the load, which is a rectangle. So the area is going to be base times height. So this load is just going to be WL. And it's going to act through the centroid. And of course, the centroid would be half the distance. In this case, it would be L over 2. Let me go ahead, too, and think ahead about what I want to do. I want to cut the structure someplace during the length, and I want to look at it at a distance x from the left-hand side. Do you want to work the left side of the cut or the right side of the cut? I think the left side will be a little easier to deal with because your distances will all be terms in x, whereas the right-hand side is going to be L minus x. So let's go with the left side. If we're going to do the left side, then I need to know my reaction at A. So let's do that. I'll sum moments now. I'll use right-hand rule for my sign convention. And since I'm trying to find the reaction at A, I'm going to sum moments at B. So there's my equilibrium statement. I'm going to sum moments at B, make sure it's an equilibrium using right-hand rule. So when I do that, about B, my concentrated equivalent force creates what kind of moment with this sign convention? Positive or negative? Positive. So it'll have a load of WL, and the distance from B to the centroid is L over 2. So there's the moment due to the applied load. And then in response to that, there's a moment generated at A, and that comes out as a negative moment, and that will be AY is the force, and the distance is X. L. So I should be able to solve for AY, and it's just going to be WL over 2. And that shouldn't be too surprising. With a symmetric load like that, you'd probably expect half the load to A and half the load to B, and half the load is WL over 2. So that's great. So then I'll come down here and draw a free body diagram for my cut. We just found the reaction, so I know that over here at A, I've got a force of WL over 2. I have a distributed load. That's intensity W. This is length X. And then at the cut, I'm looking for my moment. So there's my positive bending moment. Anybody have any questions about that? You've done this a few times, I hope, successfully. So then I'm going to want the force of this. So I'm going to deal with a concentrated equivalent force here. And again, that's a rectangular shape. It would be the base, which is x, times the height, which is w. So this force will be wx. And the distance from the cut to the centroid is half the distance. The distance is x, so this should be a distance of x over 2. So now if I sum moments this time at this cut that I made at x, and make sure this segment's in equilibrium, let's see what I have to deal with. First, I've got the internal moment, and with right-hand rule, that's a positive bending moment. What about the Wx force? It can create positive or negative bending moment about the cut. Positive. So the force will be Wx, and the distance will be x over 2. So don't forget, force times distance. And then we get over here to the reaction, and that's going to create a negative moment. So that'll be minus WL over 2, that's the force, times the distance of x. And again, force times distance. So when we're done here, we're going to get a moment expression that's equal to what? Let's see. There's a W in both terms, and there's a 2 in both terms, so I'll factor that out, W over 2. And what am I left with? I've got an x squared, so that'd be negative x squared, and then I've got a positive XL. Now, we don't usually go ahead and find the shear, so you can't check your moment equation to the shear like we did before. But you can check the moment. You know the moment a couple places in this beam. Where?
0 and 10.
Yeah, so what's the moment at x equals 0? That's A. What's the moment there? It's 0, right? You can do that by inspection. Does our equation give us that when we put in x equals 0?
Yes.
It does. We also know the moment at the other end. In this case, that would be x equal L at B, and that's also 0. So put in x equal L. Well, you get L squared minus L squared plus L squared. Yeah, 0. So that seems to be okay. We got a good moment equation. Now, you might remember in the first part of the class, for exam 1, this would be done. You're done. You've written an equation for moment. Well, now this is half the problem now. So the stakes go up a little bit, because if you miss the moment equation, well, nowhere to go. Well, there is a way to go. Down. We don't want to go down. So hopefully as time goes on, you'll get more comfortable with these and be able to generate them. So now the problem says that the slope should be the integral of the moment divided by EI dx. So there's our moment equation. So again, that W2 and that EI are all constants. I'm going to bring that out. So I'll now have W over 2EI, and then I'm looking at the integral of what's left over. In this case, it's minus x squared plus LX, and we're integrating with x. So if we do that integral, we should get W over 2EI, and then the integral of this will be minus x cubed over 3 plus LX squared over 2. There's that part, and then there's our first integration constant. Now this expression is for slope. Do I know the slope anywhere? Well, our supports, I know the slope is non-zero, so I can't evaluate it there. Over here is the same. Probably somewhere in here you know the slope would be 0. 0 slope means maximum displacement. But at this point I'm going to say, well, we don't really know, so I'm just going to leave it. Okay? So I'll go ahead and integrate now my equation for slope to get my equation for displacement. So I'm going to integrate this again. So I'm going to have W over 2EI. That's still my constant. So integrating this first term, I'm going to get minus x to the 4th over 12 plus LX cubed over 6 plus integral of C1. C1's a constant, so you integrate, you get C1x. And then you get another integration constant, C2. So those are the two constants I have to fit now, so I need two conditions. And they're both in terms of displacement. So do I know the displacement two places? Well, yeah. What's the displacement at A? 0. What's the displacement at B? 0. So let's apply those. So the displacement at x equals 0, that's A, is 0. So I plug in x equals 0 here. 0, 0, 0. All I have left is C2. So that tells me that C2 is 0. My next expression is that at x equal L, it's 0. Right? Over here at B. So I've got to put in x equal L in here and set that equal to 0. Well, let's see what we get. So I've got W over 2EI. That's my constant. And when I put in L here, what do I get? I get L to the 4th over 12, L to the 4th over 6. Well, over 6 is really 2/12. So I got negative 1/12 plus 2/12, so I get positive 1/12. So this should be L to the 4th over 12, right? And then I've got C1 times L. And that has to be equal to 0. So what value of C1 will make that equal to 0? A value of C1 equal to negative all that divided by L. So you get negative WL cubed over 24 EI. Now that I know C2 and C1, I have my expression for displacement, and I have my displacement for slope. At this point, you really have it. You could stop. If you wanted to, you could plug the C1 in here, and you'd get a long expression, and you could spend some time trying to find common denominators and all that, if you chose. You don't have to. So where do you think the maximum displacement is? Maximum displacement means what kind of slope happens at a maximum displacement? 0. So I could come up here to my slope equation and find where it's equal to 0, right? Only problem is it's a cubic equation. You guys know roots of cubic equations off the top of your head? I don't either. That would be kind of challenging, but you can do it. I will tell you that since you get 3 roots, only one of them will be in the range 0 to L. And surprise, surprise, it's going to be L over 2. It's going to happen right in the middle of the beginning. You will get another one that's probably greater than L, and you will get another one that's probably negative L, just because of the cubic nature of the cubic curve. Then once you found that distance x, say L over 2, you can plug it in this expression and find the value of the maximum displacement. Or in other ways, you just plot this curve and pick off the max. But mathematically, you could do that. But for me, if you're working the exam, we're done. You now have an expression. You can clearly see there's my equation for displacement, and you found that C2 is 0 and C1 is this value. Now, just to complete the cycle a bit, if you did plug C1 in here and find a common denominator, probably something over 24, you would get an expression that looks something like this. So that's the same problem we just worked. This is inside the front cover of your book again. I'll just have to blow it up pretty big for you to see it. So again, you can see there's the cubic nature of it, and there's that constant. That's the C2 term, and again, over a constant. They went ahead and found what the maximum value of the displacement is, because they found that the slope at L over 2. Okay? Any questions about that? Should we work some more of these? I say yes. Oh, before we go, well, no, I won't do that right yet. I'll wait.